In this video, I'll be talking about a very important algorithm that is used for exploring graphs. Exploring graphs as in, I want to walk on the edges of the graph to explore it, to see what nodes are in it, what nodes are reachable from what nodes, and so on, how many edges in it, and so on. So graph exploration is basically an algorithm that traverses the graph to collect some properties of that graph. So if I want to know what is the degree distribution, how many nodes have a certain degree, and so on. If I want to know something called community structure, if I want to know node centrality, distances, clustering coefficients, these are all graph theoretic properties. If I want to compute these, I need to explore the graph. I need to walk along the edges of the graph and explore these properties or quantify them. Another use of graph exploration is that, so suppose sometimes I want to try to quantify a property of the graph, but the graph is huge. I mean, imagine the graph has billions of nodes and billions of edges or trillions of edges. It's not proper, or it's not feasible for the graph to explore the entire graph, to visit billions of nodes and trillions of edges. One way to explore it, or to try to get an estimate of properties of that graph, is by exploring a region. So I start from one node, and then I explore some neighborhood of that node, some nodes that are its neighbors or neighbors of its neighbors, and so on. And this BFS, or breadth first search, is an algorithm for doing this exploration. In general, we can explore the graph in a deterministic way or non-deterministic way. Here I'm talking about a deterministic algorithm called BFS. There is another one that of the same family, a very similar way of working. It's called DFS, depth first search. But there's a whole field of looking at algorithms for exploring graphs in a non-deterministic ways. For example, something that we call random walks, which we will not be talking about here. In this part, we focus on the BFS algorithm. BFS is such a simple algorithm to describe and to illustrate. BFS says that if you have a graph and you want to explore it, start from a node, and take an arbitrary node and start from it, and then start visiting the neighbors of that node, then the neighbors of the neighbors, and so on. So for example, if I have this graph here, for example, and I want to explore it. So what does it mean to explore? Imagine that whenever I visit a node, I'm gonna mark it, okay? So I start with this node here. Let me actually label the nodes to make our life easier. A, B, C, D, E, F, G. So I start with node A, and I say, okay, I've explored A, I am done with it. Let me explore the neighbors of A. So now I need to look at what neighbors does A have. Okay, so now in the next level, let me mark them with blue. So in the next level, I will visit my neighbors, and they are B and C, right? So now I go to my neighbors. I have two neighbors. Now I choose arbitrarily between them. So which one I want to visit? So for example, suppose I want to visit B first. I need to look at B's neighbor. B has B's neighbors. B has A as neighbor, but A has been visited. So I say, okay, we are done with that. It has C as a neighbor. C has been visited. I'm done with that. It has E as a neighbor. It has not been visited. So let me mark it as visited. I visited it. I'm done with all the neighbors of B. Let me look at all the neighbors of C now. A is a neighbor of C, but it's been visited. B is a neighbor of C, but it's been visited. D is a neighbor of C, but it hasn't been visited. So now I say, okay, D is visited in the third layer of this visitation. So the first layer we visited A, it's in red. Second layer we visited B and C, they are both colored blue. Third layer it's D and E, they are both colored green. So now we look at the next round. So I look at D. D has two neighbors, C and E, but both have been visited, so I'm done. I'll go to E now. E has three neighbors. It has B, it's been visited. D has been visited. F has not been visited, so now I mark F. So now for the next layer, which is colored in pink, I look at it now and say, okay, now I need to visit the neighbors of F. F has E as a neighbor, but E has been visited, so I'm done. F has G as a neighbor. then I need to mark G. Then in the next layer, I will say, let me look at G and visit its neighbors. G has one neighbor. If it's been visited, all the nodes of the graphs have been visited, I am done. So this algorithm, basically the way it works is, first we start from an arbitrary node. I could have started from G, for example, but here I decided to start from A. After A, I visit A's neighbors. Here there were B and C. After that, I visit the neighbors of the neighbors that have not been visited. This will be D and E. This will be the third level of visitation here. After that, let me visit the neighbors of D and E that have not been visited. There is F. After that, let me visit the neighbors of F that have not been visited. Is G. Okay. This is how BFS works. The main detail we need to figure out is that how do we write an algorithm that will work properly like this, that once it goes from A to B, it doesn't come back to A and say, let me now mark A again, right? Because A has been marked, we have visited it already. So we need to maintain a structure that tells us that when I got to B, A has been visited, it should not be visited again, okay? And this is where we need a data structure that's appropriate for this, and the data structure that we use in BFS is called a queue. And a queue, as a data structure, is exactly the queue you would see in a store or in a cafeteria or in a restaurant. So the first person to enter the queue is usually at the head of the queue or the head of the line, is the first person to get serviced and leaves the queue. The last person to arrives into the queue is at the end of the line and gets served at the very end. This is what the queue structure. So if I want to draw it diagrammatically here, so the people or the nodes or whatever enter the queue from one side. So the first node that entered is here. The second node came after it, it's here. The third node came is here, fourth, fifth, and sixth, and so on. Now notice that they entered 1, followed by 2, followed by 3. The way they leave the queue, 1 leaves first, 2 leaves first, second, and 3 leaves third, and so on. This is the queue structure. Queue has 2 operations. So when we go to write code, for example, if I want to implement BFS in Python or Java or C, whatever language, imagine that we have a library that implements the queue data structure. That library will have to have 2 operations. One is in queue of QX, which is this one here, which basically says add X to the end of the queue. Add X to the end of the queue. DQQ, we don't need to specify X here because there's only one element that can leave the queue, which is the element at the front of the queue. So if the queue, for example, if the queue has the following here, the following elements, so we have 4, 3, 9, 1, 2, and I say D, and this is Q, and if I say DQ, Q, what this will return, it will return the value 4, okay? Because this is the element that's going to leave the queue now. So once I do DQQ, the 4 leaves the queue, and now we are left with 2, 1, 9, 3. So next time I do DQQ, 3 gets out of the queue. After that, if I do DQQ, it's the 9 that leaves. Imagine the queue is 3, 9, 1, 2, and I say in queue, Q5. What happens is that 5 gets added to the end of the queue here. So notice that 5 will not be able to get out of the queue until 3, 9, 1, and 2 have left the queue in that specific order. So we use the queue for this matters, that when I start with a node and I want to visit its neighbors, as I visit its neighbors, the order I visit, so if I visit B, C, D, I put B on the queue, then C on the queue, then D on the queue. In the next round, I remove a node from the queue and visit its neighbors. Now notice what happens is that the neighbors of the neighbors will go to the back of the queue, okay? So if we look at the pseudocode of the breadth first search, how the algorithm would work, it's as follows. Again, I have the name of the algorithm BFS. It takes as input a graph, and it takes a designated start node. So I have to have a node from which I start the search. And just as I was labeling nodes here, so what's the output? For every node, I will have label of true or false. True if the node has been visited by the end of running the algorithm, false if it hasn't been visited. What happens now? How does it work? On lines 1 and 2, here I say that let me initialize everything to not visited. I know that I haven't visited anything. Let me actually denote that v of j is false for every node j. So no node has been visited. Next, the line 3, I say vi is true. So node I is visited. Why is node I visited? Because it's the source node. Okay, it's part of the input. So now here I start the visiting. So in round 1, I declare that I have visited node I. Then what do? Now I start looking at the queue. The queue is empty in the beginning. I put I on the queue here. I put I in the queue. So this is the first node. The queue will have only one node in it, which is I. Then I remove I from the queue. I remove I from the queue. This is what's going to happen in this line, even though it's written JDQQ, but J in the very first iteration is going to have the node I in it. Then for every neighbor H of J, if it hasn't been visited, I will declare it visited and I will put it on the queue. For every neighbor that has not been visited, I will declare it as visited and put it on the queue. Okay, this is how the algorithm works. At the end, I return this information about every node, if it's been visited or not. Okay, let's try to illustrate this algorithm here. Again, so suppose I'm going to draw a smaller graph here. So if this is node A and B and C, node D here. So this is, and suppose that the node I, in this case, I will start with A. So when I come to line 5 here, let me start with 5, the queue, and when after I execute line 5, the queue has just one thing in it, which is the node A. Then when I come to this loop, I say, okay, the queue is not empty. Let me get an element on line 7. Let me get an element from this queue and put it in J. So J now has the node A in it. Okay, this is based on line 7. On line 8, I look at all the neighbors H of J. So H can be B or H can be C. These are the only neighbors of A. If V of H is false, now I know that they are both false, they haven't been visited. I will declare them. So now V of A was set to true here. V of B was false, and V of C was false, and V of D was false. So now when I get to line 9, 8 and 9, I will look at all neighbors of A. I will look at them and say, okay, there are B and C. For any of these two nodes, if V of that node is false, I turn it into true and I put the node into the queue. Now notice that the queue on line 7, once J is equal to A, the queue now is empty, right? Because we removed A from it. When I go to line 9 and 10 and 11, what happens now is that V of B becomes true, V of C becomes true, and the queue now is B is at the head of the queue and C at the end of the queue. If I visited them in that order, if I visited the C first and B second, then C is at the head of the queue and B is at the back. So Q will have B and C. Then I go back to the loop on line 6. The queue is not empty. I say, let's remove an element from the queue. In this case, we remove B. J equals B. And now the queue has one element in it equals C. So now I look at every neighbor of B. C is one of them. But this line here says if V of C is false, if V of C is true, don't do any of the things on lines 10 and 11. Since V of C is true on line 9, then we don't do anything. Then I go to the next neighbor of B, which is D. Actually, I go to the neighbor of B, that's A. Also, V of A is true. Therefore, lines 10 and 11 don't do anything. Then I go to neighbor D of B. Neighbor D of B, the V of D is false. Therefore, I now turn it into true. And I put D onto the queue. Now, look where the D is going to be on the queue. it's going to come after C. So this Q ensures now that C has to be dealt with before D, which is very important because I wanted to handle the neighbors of A before the neighbors of the neighbors of A. And this Q is going to ensure this. I will visit C. I will deal with C before I deal with D. So now I go back to line 6 and I see, okay, the queue is not empty. I say let me remove a node from here. So J is C now, and the queue that has only D on it. I look at all the neighbors of C. I find that all of them V for the node is true. There's nothing to do here. I come back to the loop on line 6 and I say, okay, let me remove the node from Q, which is D. The Q is now empty. And now I say, okay, let me look at all the neighbors of D, which is the line 8. For all the neighbors, V for that node is true. There is nothing to do. Now I go to line 6. Line 6 now is the condition there is false because it says while Q is not empty, but the Q is empty, therefore I am done. So this is how the algorithm terminates. So it visits A, then visits B and C, then visits D. Now, when is it possible for the algorithm to return V to be false for any nodes? Only if the graph is not fully connected. If there are some nodes that are not reachable from A, by the time this algorithm terminates, the value for these nodes is going to be false. Okay. What is the running time of BFS? I will start first with actually a loose analysis. And so let's assume that we have a adjacency list and the graph has n nodes and m edges. Let's look at the worst case analysis of this. So this loop here on lines 1 and 2, the line 2 takes one operation, but line 1 takes on the order of n operations, right? So line 1, it's going to loop over n nodes. For each one of these nodes is going to do a constant number of operations on line 2. Line 3 is going to do a constant number of operations. Line 4, it's a constant number of operations. It's just initializing Q to empty. Line 5 is just adding one element to the queue. That's one operation. And now we start with the loop on line 6. Now let's look at the loop on line 6. And here, while the queue is not empty, of course, we have one node there at the beginning. But if we think about it, every node, if the graph is connected, every node is going to be added to the queue and removed to the queue. So this in the worst case, this performs on the order of n. Because think about it, if the graph is connected, every node is going to be added to the queue once and removed from the queue once. So the queue in the worst case, if we think about it total number of times, we will have n nodes in it, okay? The line 7 takes O of 1 operation. What's the number of neighbors of J? So line 9 now, line 8, sorry, for each neighbor H of J. How many neighbors can the graph have? Okay, how many neighbors can the node have? Well, if you think about it, a node, if the graph has n minus 1 nodes and m edges, one loose analysis, one can say, I cannot have more than m neighbors. If the graph has m edges, I cannot have more than m neighbors, because to have a neighbor, I have to have an edge. Another loose analysis, I could have said it's O of n. Why? Because a node in a graph with n nodes cannot be connected to more than n minus 1 nodes, right? So in the worst case, the node is connected to every other node, but every other node, there are n minus 1 of them. So in a loose analysis, let's assume it's O of m or O of n. These lines here, all of them take O of 1, and this takes O of 1 here. So based on this loose analysis, lines 1 to 5, all of these take O of n. Right? So the first two lines took O of n, and then we are just adding O of 1. Lines 6 to 11, now we have the outer loop on line 6 taking O of n, and the inner loop on line 8 taking O of m or O of n. So let's assume actually it is the O of m. Then line 8 is taking O of m, line 6 is taking O of n. So this is going to take O of n times m. And the line 12 takes O of 1. So now we have the running time of this is O of n plus O of n m plus O of 1. And if you think about it, this is O of n m. Okay? So that one simple or loose analysis of BFS tell me that it takes O of n times m. Can we do better? And is BFS faster than this? The answer is yes. But to get the tighter analysis, you have to think carefully and you have to reason carefully about how the algorithm works. And here you need to think about, if you have a graph, suppose we have a graph like this, A, B, C, D, E. Think about how many times if every edge is going to be inspected by BFS. So if we think about it, when we start the algorithm from A, the edge from A to B is going to be inspected once because we are looking at the neighbors of A. The edge from A to C will be inspected once because AC is one of the neighbors of A. Now let's look at B. When we are working with B, we are going to be inspecting the edge from B to A, again, because A, it's its neighbor. There is no more edges to inspect there. When we look at C, the edge from C to A is going to be inspected because A is a neighbor. The edge from C to D is going to be inspected because D is a neighbor. The edge from C to E is going to be inspected because E is a neighbor. When I work with D, the edge from D to C is going to be inspected because C is a neighbor. When I work with E, the edge from E to C is going to be inspected because C is a neighbor. And that's it. Now look at this figure and see how many tick marks are on every edge. You will see that every edge is visited exactly twice. Every edge is visited exactly twice. So if we have m edges, and you reason about it like this whole thing here ends up taking O of m. Okay? So if you reason about it carefully, the way I just reasoned about it and asked your question about every edge, how many times was it visited, you will find that every edge was visited twice. For every time we visit the edge, we do a constant number of operations. Therefore, it is some 2 times m times some constant operation. This is from line 6 to 11, but this is O of m, and this is why I wrote that. We have O of n here. Therefore, we get a better analysis that tells us it is O of n plus m. And this is the official running time of BFS. If someone asks you what's the running time of BFS, it is linear in the number of nodes and edges. On the previous slide, we did a loose analysis and we showed O of n times m. But again, that's a loose analysis. If you run the algorithm and you time it and you plot the running time, you will notice that it grows linearly with the number of edges and the number of nodes.